Look around you, and you will notice a strange pattern. From the tiny marbles of planets to the massive burning spheres of stars, the universe seems obsessed with one shape: the circle, the sphere, the round. But why? Why is everything in the universe round? And what is gravity hiding from us? Think about it for a moment. Why is the Earth not a cube? Why is the sun not a giant pyramid? Why is the moon not shaped like a pancake? These are not silly questions. They are some of the deepest questions you can ask about the way the universe works, and the answers will take us on a journey through space and time, through the birth of stars and the death of worlds, all the way to the strangest objects in the cosmos. So tonight, wherever you are, whatever time it is, let yourself settle in. Maybe you are lying in bed. Maybe you are resting on a couch. Maybe you are looking out a window at a sky full of stars. Whatever the case, take a breath. Let your body relax. Because what we are about to explore together is one of the most beautiful secrets of the universe. It is a secret written into the very fabric of space itself. And once you see it, you will never look at the night sky the same way again. Let us begin with something simple. Something you can see right now if you step outside and look up. The moon, that glowing circle in the sky. It looks so perfectly round, so smooth, so calm. But here is the thing. The moon is not actually a perfect circle. It is not even a perfect sphere. It has mountains. It has craters. It has valleys and ridges and plains of ancient volcanic rock. And yet, from a distance, it looks like a marble, a perfect glowing marble hanging in the darkness. Why? The answer starts with a force you feel every single second of your life, even right now as you listen to these words. Gravity, that invisible hand that keeps your feet on the ground, that keeps the water in your glass, that keeps the air in your lungs. Gravity is everywhere. And it is the reason everything in the universe tends toward a very specific shape. But gravity is not just a simple pull. It is something far more mysterious and far more powerful than most people realize. To understand why the universe loves round things, we need to understand what gravity actually does. And we need to go deeper than you might expect. Let us start with a thought experiment. Imagine you have a huge pile of dirt floating in space. Just a big, messy, shapeless pile of rocks and dust and soil. No air around it, no ground beneath it. Just this cloud of material hanging in the emptiness. Now, what would happen to this pile over time? At first, nothing obvious. The rocks just float there. But here is what most people do not realize. Every single piece of that dirt is pulling on every other piece. Every rock is tugging on every grain of sand. Every speck of dust is reaching out with its own tiny, invisible gravitational hand and saying, "Come closer." And slowly, very slowly, all that material starts to move. The outer pieces drift inward. The loose bits fall toward the center. And as more material gathers in the middle, the pull gets stronger, which pulls in even more material, which makes the pull even stronger. It is a cycle that feeds itself. Now here is the key. Gravity does not pull in just one direction. It does not only pull things down, or left, or right. Gravity pulls equally from all directions toward the center. Think about that. From every single direction, gravity is pulling everything toward one central point, from the top, from the bottom, from the sides, from every angle you can imagine, all at once. So what shape do you get when something is being squeezed equally from all directions? A sphere. That is the answer. And it is so simple that it almost feels like it cannot be the whole story. But it is. Gravity pulls things equally toward a center. And the most natural shape that results from equal pulling in all directions is a round one, a sphere. But wait, if that is all there is to it, then why are some things in space not round? Why are asteroids lumpy? Why are comets shaped like potatoes? Why do some moons look like they were chewed on by a dog? This is where things get really interesting. You see, gravity is not the only force in the universe. There are other forces too, and for small objects, those other forces are actually stronger than gravity. Think about a rock sitting on your desk. That rock is not being crushed into a sphere by its own gravity. Why not? Because the rock is strong enough to resist its own gravitational pull. The chemical bonds that hold the rock together, the rigid structure of its minerals, these are powerful enough to say no to gravity. The same is true for small objects in space. An asteroid that is only a few miles across does not have enough gravity to overcome the strength of the rock it is made from. So it stays lumpy, it stays odd-shaped. It keeps whatever shape it had when it was formed, or whatever shape it got smashed into by a collision. But here is the rule. The bigger something gets, the stronger its gravity becomes. And at a certain size, gravity wins. The rock can no longer hold its shape. The material gives in, it flows, it shifts, it rearranges itself. The high spots get pulled down, the low spots get pushed up. And the whole thing slowly, over millions of years, settles into the shape that gravity demands. A sphere. Scientists have a name for this tipping point. They call it hydrostatic equilibrium. It is a fancy term, but the idea is simple. Hydrostatic equilibrium is the point at which an object is so massive that its own gravity can mold it into a round shape. It is the point at which gravity wins the battle against the strength of rock and ice and metal. For objects made of ice, this happens at a size of about 400 kilometers across. For objects made of rock, it takes a bit more, somewhere around 600 kilometers or so. And for anything bigger than about 800 kilometers across, no matter what it is made of, gravity has already won. The object is going to be round. This is why the planets in our solar system are all round. Earth, Mars, Jupiter, Saturn, all of them. Tired of waking up at 3 a.m. because your sleep video ended? Cosmic Drifts Beyond the Stars plays for hours. No ads, no interruptions, no reaching for your phone. 5 full night sleep experiences, one-time purchase. Begin now at mycosmicdrift.com. They are all massive enough that their gravity has pulled them into spheres. Even Pluto, which was famously demoted from planet status, is still round, because it is big enough for gravity to have done its work. But asteroids like Vesta and Pallas, which are only a few hundred kilometers across, are not quite round. They are in the middle zone, big enough for gravity to have started rounding them off, but not quite big enough for the job to be finished. And here is something wonderful to think about. This process is not instant. It takes time, a lot of time. When a planet first forms, it is not a perfect sphere. It is a hot, messy, swirling ball of molten rock and metal. It takes millions of years for all that material to settle down, to cool, to flow into the shape that gravity wants. And even then, it is not perfectly round, because there is another force at work: spin. Almost everything in the universe spins. Planets spin, stars spin, galaxies spin. And when something spins, it creates a force that pushes outward at the equator. You have felt this force yourself. Think about what happens when you spin around in a circle. You feel a pull outward, away from the center. That is the same force that acts on a spinning planet. And this force changes the shape of round things in space. Instead of being perfect spheres, spinning objects become slightly squished. They bulge out at the equator and flatten at the poles. Scientists call this shape an oblate spheroid. It is still basically round, but a little wider in the middle than at the top and bottom. Earth is like this. If you could measure very carefully, you would find that Earth is about 43 kilometers wider at the equator than from pole to pole. That does not sound like much for a planet that is almost 13,000 kilometers across, but it is there. Earth is not a perfect sphere. It is a slightly chubby sphere. Saturn is much more dramatic. Saturn spins very fast, completing one rotation in just over 10 hours. And because Saturn is mostly made of gas, which is easy to squish and stretch, it has a very noticeable bulge. Saturn's equator is almost 12,000 kilometers wider than the distance between its poles. If you look at Saturn through a good telescope, you can actually see that it is not perfectly round. It is visibly squished, like someone sat on a ball. And some stars are even more extreme. There is a star called Altair that spins so fast that its equator is about 25% wider than the distance from pole to pole. If you could see Altair up close, it would look like an egg or a flying saucer. So the universe's love of round shapes is real, but it is not a love of perfect rounds. It is a love of nearly round shapes, modified by spin. Gravity wants a sphere. Spin wants a bulge. The final shape is a compromise between the two. Now, let us go deeper, because so far, we have been talking about gravity as if it were just a simple pulling force, as if gravity were just an invisible rope attached to every piece of matter, tugging everything toward every other piece. And that is basically how Isaac Newton described gravity over 300 years ago. He said that every object with mass pulls on every other object with mass, and that this pull gets weaker as objects get farther apart. Newton's description of gravity works amazingly well. It is how we calculate orbits. It is how we send spacecraft to other planets. It is how we predict where the moon will be next Tuesday. But here is the thing. Newton could never explain why gravity works. He could tell you how strong it was. He could tell you how it changed with distance. But he could not tell you what gravity actually is. What is this invisible force? How does the Earth know the moon is there? How does gravity reach across the emptiness of space and grab hold of things? Newton himself admitted this was a problem. He wrote about it in his famous book, and he basically said, "I have no idea why this happens. I can describe it, but I cannot explain it." For over 200 years, nobody could. And then along came Albert Einstein. In 1915, Einstein published his theory of general relativity, and it changed everything we thought we knew about gravity. What Einstein showed is that gravity is not really a force at all, not in the way we usually think of forces. Instead, gravity is something much stranger, much more beautiful, and much more connected to the roundness of the universe. Einstein showed that space itself is not just an empty stage on which things happen. Space is a real thing. It has properties. It can bend. It can stretch. It can warp. And massive objects cause space to warp around them. There is a famous way to picture this. Imagine stretching a large rubber sheet out flat, like a trampoline. Now place a heavy bowling ball in the center. What happens? The sheet sags. It curves downward around the bowling ball, creating a dip, a valley in the fabric. Now roll a marble across the sheet. The marble does not travel in a straight line. It curves. It rolls toward the bowling ball, not because the bowling ball is pulling on it with some invisible force, but because the marble is following the curve of the sheet. It is rolling along the dip that the bowling ball created. That is what gravity is, according to Einstein. Massive objects like stars and planets warp the fabric of space around them, and other objects follow the curves in that warped space. The Moon orbits Earth not because Earth is pulling it with some mysterious force, but because Earth has warped the space around it, and the Moon is following the curved path through that warped space. And here is the connection to roundness. When a massive object warps space around it, it does so equally in all directions. The dip in the fabric of space is not deeper on one side than the other. It is symmetric. It is round. The warping of space around a star or planet is spherical. So the roundness of objects in space is not just about the shape of the objects themselves. It is about the shape of space itself. Space is curved into round shapes by the matter within it. The universe is round all the way down, from the shape of planets to the shape of the invisible fabric they sit in. This is what the title of our journey meant by the secret shape of gravity. The secret is that gravity is not just a force. It is a shape. It is the shape of space itself, curved and warped by matter. And that shape, at its most fundamental level, is round. Now let us sit with that idea for a moment, because it is worth appreciating. Every time you see a round planet in the sky, you are seeing a physical expression of the way space itself is curved. The roundness of Jupiter is not just the result of gravity pulling gas inward. It is a reflection of the geometry of the universe. It is the universe's own shape made visible. That is beautiful, is it not? But we are far from finished, because the story of roundness goes much deeper than planets and stars. To really understand why the universe loves spheres, we need to explore the actual physics of how round things form. We need to watch gravity at work in real time, sculpting worlds out of chaos. Let us go back to the very beginning, not the beginning of Earth, not even the beginning of the solar system. Let us go back to the beginning of everything, the birth of the universe itself. About 13.8 billion years ago, the universe began in an event we call the Big Bang. In the very first moments, there was no structure, no stars, no planets, no galaxies. There was only energy expanding outward in all directions. And as this energy cooled, it began to form the simplest elements: hydrogen, helium, a tiny bit of lithium. That was it. The entire universe was made of these three elements, spread out in a vast, thin cloud. But this cloud was not perfectly smooth. There were tiny ripples in it, tiny differences in density, where one region had just a little more matter than the region next to it. And these tiny differences were enough for gravity to start working. The regions with slightly more matter had slightly more gravitational pull. They attracted more material from their surroundings. As they grew, their pull got stronger. They attracted even more material. And over hundreds of millions of years, these regions grew into enormous clouds of gas, clouds that would eventually collapse under their own gravity to form the first stars. Now, let us watch one of these clouds collapse. Imagine a vast cloud of hydrogen gas spread out over many light years. At first, it just sits there. The atoms bounce around gently. The cloud has no real shape. It is just a shapeless fog. But gravity is patient. And slowly, the atoms in the denser parts of the cloud begin to drift closer together. As they do, the gravitational pull in those regions gets stronger. More atoms are pulled in. The cloud begins to shrink. And here is something wonderful. As the cloud shrinks, it does not collapse into a flat disk or a long tube or a cube. It collapses roughly equally from all sides. Because gravity, remember, pulls from all directions toward the center, so the cloud shrinks into a roughly spherical shape. This is the birth of a star, a massive ball of gas, collapsing under its own gravity, getting hotter and denser at its core. And eventually, the temperature and pressure at the center become so intense that hydrogen atoms begin to smash together. They fuse, they merge, and when they do, they release an enormous amount of energy. Light, heat, radiation. A star is born, and it is born round. But the star is not round just because gravity pulled it into a sphere. The star is round because it has achieved a delicate balance. Gravity is pulling everything inward, trying to crush the star down to a single point. But the energy from nuclear fusion at the core is pushing outward. It creates pressure, radiation pressure, heat pressure, the outward push of all that energy being released. And these two forces, gravity pulling in and pressure pushing out, reach a balance, an equilibrium. And the shape that this balance takes is a sphere, because the inward pull of gravity is equal in all directions, and the outward push of pressure is also equal in all directions. The only shape that balances equal forces from all directions is a sphere. This is hydrostatic equilibrium again. But now we are seeing it on a grander scale. Not just a cold rock being pulled into a round shape, but a blazing furnace of nuclear fire, balanced on the edge between collapse and explosion. And that balance takes the shape of a sphere. Every star in the sky right now is in this state. Our sun is in this state. It is a sphere because gravity and pressure have reached a truce. Gravity says collapse. Pressure says expand. And the result is a glowing ball, hanging in space, balanced and round. But what happens when this balance breaks? That is where the story gets truly dramatic. Stars do not live forever. They burn through their fuel. And what happens when the fuel runs out depends on how big the star was to begin with. For a star like our sun, the end is relatively gentle. When the sun runs out of hydrogen fuel in its core, about 5 billion years from now, it will swell up into a red giant. It will expand so much that it might swallow Mercury, Venus, and possibly even Earth. But eventually, the outer layers will drift away into space, forming a beautiful cloud called a planetary nebula. And at the center, the core of the sun will be left behind, a dense, hot, glowing ember about the size of Earth. This is called a white dwarf, and it is round, incredibly round, because even though the nuclear fire has gone out, gravity is still pulling everything inward. And the only thing stopping the white dwarf from collapsing further is the pressure of electrons pushing against each other. They refuse to be squeezed any closer. This electron pressure holds the white dwarf up, and once again, the balance between inward gravity and outward pressure creates a sphere. A teaspoon of white dwarf material would weigh about 1 ton. That is how dense this material is. All that matter crammed into a sphere the size of our planet. It is like taking the sun and squishing it down to the size of Earth, and gravity keeps it perfectly round. But for bigger stars, the story has a more dramatic ending. When a star that is much more massive than our sun runs out of fuel, the collapse is catastrophic. The core falls inward so fast that it triggers a massive explosion called a supernova. For a few weeks, the exploding star can outshine an entire galaxy of hundreds of billions of stars. It is one of the most violent events in the universe, but the core survives. Or rather, it transforms. In the incredible crush of the collapse, atoms themselves are destroyed. Electrons are smashed into protons, and what is left is a ball made almost entirely of neutrons. A neutron star. Neutron stars are mind-bendingly dense. Imagine taking our entire sun and crushing it down into a sphere the size of a city. That is what a neutron star is. A ball maybe 20 kilometers across that weighs more than the sun. A single teaspoon of neutron star material would weigh about 1 billion tons. That is more than the weight of every car, every building, every mountain on Earth combined. And gravity holds this material in a sphere so perfect that the tallest mountains on a neutron star are probably less than 1 millimeter high. Think about that. On Earth, mountains can reach almost 9 kilometers into the sky. On a neutron star, the gravity is so strong that the tallest bump on the surface might be smaller than a grain of sand. That is how desperately gravity wants things to be round. On a neutron star, gravity is about 2 billion times stronger than on Earth. It flattens everything. It smooths everything. It forces the entire object into the most perfect sphere in the known universe. Neutron stars spin incredibly fast too. Some of them rotate hundreds of times per second. Imagine a ball the size of a city, heavier than the sun, spinning around hundreds of times every single second. Even at that speed, the bulging at the equator is tiny compared to the size of the star, because gravity is so overwhelmingly strong that even the spinning cannot distort the shape very much. So we have seen gravity create round shapes at every scale. Planets, stars, white dwarfs, neutron stars. Each one is round because of the same basic principle. Gravity pulls equally from all directions toward the center, and the resulting shape is a sphere. But there is one more place we need to go, one more object we need to visit, the ultimate expression of gravity's obsession with roundness. An object where gravity has won so completely, so totally, that nothing else matters. Not pressure, not spin, not the strength of matter itself. We need to talk about black holes. A black hole is what happens when gravity has no rival, when there is no force left to push back, when the collapse just keeps going and going and going until all the matter in a star is crushed down to a point of infinite density. A point so small and so dense that the laws of physics as we know them break down entirely. But before we get to that terrifying center, let us talk about the outside of a black hole, because the outside has a shape, and that shape is, you guessed it, a sphere. The boundary of a black hole is called the event horizon. It is not a physical surface. You cannot touch it or stand on it. It is simply the point of no return. The distance from the center of the black hole at which gravity is so strong that even light cannot escape. And this boundary forms a perfect sphere around the center. Think about that. The event horizon is the ultimate expression of gravity's symmetry. Gravity pulls equally from all directions, and so the boundary where things cannot escape is equidistant from the center in every direction. It is a sphere, a perfect, invisible, inescapable sphere. The size of this sphere depends on how much mass is in the black hole. For a black hole with the mass of our Sun, the event horizon would be a sphere about 6 kilometers across. That is it. The entire mass of the Sun, compressed until the point of no return, is just 3 kilometers from the center. For Earth, if you could somehow crush all of its matter into a black hole, the event horizon would be about the size of a marble, less than 2 centimeters across. All the mountains, all the oceans, all the continents, everything, compressed until the point of no return, is smaller than your fingertip. For the supermassive black holes at the centers of galaxies, the event horizon is much larger. The black hole at the center of our Milky Way has about 4 million times the mass of the Sun, and its event horizon is a sphere about 24 million kilometers across. That sounds huge, and it is. But compared to the galaxy itself, it is tiny, and it is perfectly round. In 2019, scientists with the Event Horizon Telescope project captured the first ever image of a black hole. It was the supermassive black hole at the center of a galaxy called M87. And what did they see? A dark circle, surrounded by a glowing ring of hot gas. The dark part was the shadow of the event horizon, and it was round, almost perfectly round. This was not a surprise to physicists. They had predicted it for over 100 years, but seeing it with real data, captured by telescopes spread across the entire Earth, was something else entirely. It was proof, visible, stunning proof that gravity shapes the universe into spheres, even at the most extreme scales. Now, let us go even deeper into the black hole, past the event horizon, into the unknown. According to Einstein's equations, once you cross the event horizon, there is no way out. You are falling toward the center, and at the center, all the matter that created the black hole has been crushed to a single point, a point with zero size and infinite density. Physicists call this the singularity. The singularity is where our understanding of physics breaks down. We do not really know what happens there. Our equations give us infinities, which usually means we are missing something. Many physicists believe that to truly understand the singularity, we need a new theory, a theory that combines Einstein's general relativity with quantum mechanics, a theory of quantum gravity. But here is what we do know. Everything about the black hole from the outside is spherical. The gravitational pull is spherical. The event horizon is spherical. The warping of space around it is spherical. Even the way light bends and circles around the black hole happens in patterns that are governed by the symmetry of a sphere. The black hole is gravity taken to its extreme. And at its extreme, gravity is a sphere. Now, I want to take a moment to step back and appreciate something. We have traveled from piles of dirt floating in space to the most extreme objects in the universe. And at every step, the answer to the question, what shape does gravity make, has been the same, a sphere. From asteroids that are just barely big enough for gravity to round them off, to planets with their mountains and valleys, to stars burning with nuclear fire, to white dwarfs glowing with leftover heat, to neutron stars spinning at impossible speeds, to black holes swallowing light itself. At every scale, gravity wants one thing, round. And the reason is always the same. Gravity pulls equally from all directions. The only shape that satisfies this equal pulling is a sphere. It is the most efficient shape, the most balanced shape, the shape of least resistance, the shape that nature chooses when given no other option. But now I want to take you somewhere unexpected, because the universe's love of round shapes is not just about gravity. There is another place where we see perfect spheres in nature, and it has nothing to do with gravity at all. Soap bubbles. Think about a soap bubble floating through the air. It is round, almost perfectly round. But a soap bubble is far too small for gravity to have any effect on its shape. So why is it a sphere? The answer is surface tension. The molecules in the soap film are attracted to each other. They want to be as close together as possible. And the way to minimize the surface area of a film that encloses a given volume of air is to make that film into a sphere. In other words, a soap bubble is round for the same mathematical reason that planets are round, not because of the same force, but because of the same principle. When something is being squeezed or pulled equally from all directions, the result is a sphere. For planets, the squeezing comes from gravity. For soap bubbles, it comes from surface tension. But the geometry is the same. This is one of the most beautiful ideas in all of physics. Different forces, operating at completely different scales, producing the same shape. The sphere appears again and again in nature, not because of any one particular force, but because of a deeper mathematical truth. The sphere is the shape of symmetry, the shape of equality, the shape you get when there is no preferred direction. Think about that for a moment. A sphere has no top or bottom, no left or right, no front or back. Every point on its surface is the same. Every direction from its center is the same. It is the most democratic shape in the universe, and that is why nature loves it. Water drops, floating in zero gravity, form spheres. Mercury beads on a table form spheres. Stars form spheres. Planets form spheres. Even the observable universe itself may be shaped like a sphere, expanding outward equally in all directions from the point of the Big Bang. Roundness is not just a shape, it is a principle. It is nature saying, when everything is equal, when no direction is special, when there is no bias or preference, the result is a sphere, and gravity is the great equalizer. It pulls from all directions with equal strength. It does not care about up or down, left or right. It only cares about distance from the center. And so everything it touches, everything it shapes, everything it sculpts over billions of years ends up round. Now, let us explore some of the most fascinating details of this cosmic sculpting process. Because while the big picture is simple, the details are full of surprises. Let us talk about the Earth, our home, the planet we live on. We all know it is roughly round. But how round is it, really? If you shrunk the Earth down to the size of a basketball, would you be able to feel the mountains and valleys? Would Mount Everest be a noticeable bump? Would the Mariana Trench be a noticeable dip? The answer might surprise you. Mount Everest is about 8.8 kilometers tall. The Mariana Trench is about 11 kilometers deep. That is a total range of about 20 kilometers from the lowest point to the highest point on Earth. But Earth's diameter is about 12,142 kilometers. So that 20-kilometer range is only about 0.16% of the total diameter. That is incredibly small. If you shrunk the Earth to the size of a basketball, the mountains and ocean trenches would be smaller than the bumps on the basketball's surface. In other words, the Earth is smoother than a basketball. Gravity has done such an effective job of pulling everything into a sphere that even the tallest mountains are nothing more than tiny pimples on a nearly perfect ball. And here is why. Remember what we said about gravity and the strength of rock. For small objects, rock is strong enough to resist gravity. That is why asteroids can be lumpy. But for something the size of Earth, gravity overwhelms rock. If a mountain gets too tall, the weight of the rock at the base becomes so great that the rock starts to flow. It deforms. It sinks. The mountain literally cannot support itself. There is a limit to how tall a mountain can be on any given planet, and that limit depends on the strength of gravity and the strength of the rock. On Earth, with our particular gravity and our particular kind of rocks, the maximum height for a mountain is somewhere around 10 to 15 kilometers, which is right about where Mount Everest sits. On Mars, gravity is weaker, only about 38% of Earth's gravity. So mountains can be taller before they start to sink under their own weight. And indeed, Mars has the tallest known mountain in the solar system, Olympus Mons. It is about 22 kilometers tall, almost 3 times the height of Everest. But even Olympus Mons is tiny compared to the overall size of Mars. And Mars, like Earth, is essentially a smooth sphere when seen from space. This is gravity at work, patient, persistent, always pulling, always smoothing, always rounding. Now let us talk about something else that affects the roundness of planets: the material they are made of. We have already mentioned that icy objects become round at smaller sizes than rocky objects. This is because ice is softer than rock. It flows more easily under pressure, so gravity can mold it into a sphere without needing as much mass to overcome the material's strength. This is why some of the moons of the outer solar system are round, even though they are relatively small. Saturn's moon, Mimas, for example, is only about 400 kilometers across. That is tiny, but it is made largely of ice, and ice gives in to gravity more easily than rock, so Mimas is round. Well, mostly round. It has an enormous crater on one side that makes it look remarkably like the Death Star from the movies, but overall, its shape is spherical. Compare that to Vesta, the second largest asteroid in the asteroid belt. Vesta is about 525 kilometers across, larger than Mimas, but Vesta is made of rock, which is stronger than ice. And so Vesta is not quite round. It is close. It is in that transition zone. But gravity has not quite won the battle against the strength of Vesta's rocky body. Then there is Ceres, the largest object in the asteroid belt, at about 940 kilometers across. Ceres is round. It is the smallest known body that has clearly achieved hydrostatic equilibrium. In fact, this was one of the criteria used when the International Astronomical Union defined what a dwarf planet is. A dwarf planet must be massive enough for its own gravity to pull it into a nearly round shape. Ceres meets this requirement. So Ceres is officially a dwarf planet, not just an asteroid. So the boundary between lumpy and round is not a sharp line. It is a gradual transition that depends on what the object is made of, how warm it is, and how long gravity has had to do its work. But the general rule holds. Get big enough, and you will be round. Gravity guarantees it. Now, let us turn our attention to something even more amazing. We have talked about how gravity shapes solid objects like planets and asteroids, but gravity also shapes liquids and gases. And when it does, the results can be stunning. Think about the sun. The sun is not solid. It is a giant ball of gas, mostly hydrogen and helium. It has no solid surface, no mountains, no valleys, just gas and plasma, all the way through. And yet the sun is almost perfectly round. In fact, the sun is one of the most perfectly round natural objects ever measured. Its equatorial diameter is only about 10 kilometers larger than its pole-to-pole diameter. That is a difference of about 0.0001%. For something that is 1.4 million kilometers across, that is astonishingly round. Why is the sun so round? Because gas is easy to mold. Unlike rock, which has structural strength and can resist gravity to some degree, gas has almost no resistance. It flows freely. It responds to forces instantly. And so gravity has an easy time pulling it into a perfect sphere. There is nothing to fight back, nothing to create bumps or lumps, just gas, flowing obediently into the shape that gravity demands. The same is true for the gas giant planets. Jupiter and Saturn are mostly made of hydrogen and helium gas, just like the Sun, and they would be almost perfectly round if they were not spinning so fast. It is the spin, not any resistance of the material, that makes them slightly squished. Jupiter rotates once every 10 hours. That is incredibly fast for something so large. Jupiter's equator is moving at about 45,000 kilometers per hour. At that speed, the outward push at the equator is strong enough to make Jupiter about 7% wider at its equator than from pole to pole. That is a noticeable bulge. But still, Jupiter is fundamentally round. Gravity has done its job. Only the spin has prevented a perfect sphere. Now, there is one more aspect of gravity's love of roundness that I want to explore with you. And it goes beyond individual objects. It is about the large-scale structure of the universe itself. When you look at the universe on the very largest scales, you see that matter is not evenly distributed. It is arranged in a vast cosmic web of filaments and walls, with huge empty voids between them. Galaxies cluster together along these filaments, like dewdrops on a spider's web. But look at an individual galaxy cluster, the largest gravitationally bound structures in the universe. What shape are they? Many of them are roughly spherical. Galaxy clusters are collections of hundreds or thousands of galaxies, all held together by gravity, and the hot gas that fills the space between the galaxies, the intracluster medium, is in a state of hydrostatic equilibrium, just like a star. The gas is being pulled inward by gravity and pushed outward by its own pressure, and the result is a roughly spherical distribution of matter. Even on the larger scales, gravity wants things to be round. Now let us talk about something that connects all of these ideas together, something that brings the story of roundness full circle, if you will forgive the pun. Earlier, we talked about Einstein's vision of gravity as the curvature of space itself, and we used the analogy of a bowling ball on a rubber sheet. But I want to push that idea further, because the curvature of space is not just an analogy, it is a real, measurable property of the universe. And it has direct consequences for the shapes we see around us. When a massive object curves the space around it, that curvature does not just affect how objects move, it also affects how time flows. Near a massive object, time actually passes more slowly than it does far away. This is not science fiction. It is a measurable, proven fact. The clocks on GPS satellites, which orbit high above the Earth, tick slightly faster than clocks on the ground. This is because they are farther from Earth's mass and therefore in a region where space is less curved. The difference is tiny, just a few millionths of a second per day. But it is real. And if GPS systems did not account for this time difference, your navigation would be off by several kilometers. So, when we say that gravity warps space, we mean it literally. Space and time are both affected. Near a massive object, space is curved and time is slowed. And both of these effects are spherically symmetric, meaning they are the same in all directions from the center of the mass. This is why the orbits of planets are the shapes they are. A planet orbiting a star is following a path through curved space, and because the curvature is spherically symmetric, the orbit wraps around the star in a regular, predictable way. The planet traces out an ellipse, a slightly squished circle, as it moves through the curved space around the star. Everything about gravity's effects on space is round. The curvature is round. The time dilation is round. The orbits are round. The event horizons of black holes are round. It is roundness all the way down. And this brings us to one of the most profound ideas in all of physics, the idea that the laws of the universe do not favor any particular direction. There is no preferred up or down in the universe. There is no special direction that gravity prefers. Gravity treats all directions equally. This principle is called isotropy. It means the same in all directions, and it is one of the foundational principles of modern physics. The universe, on large scales, is isotropic, the same in every direction. And when you have a force that is isotropic, that treats all directions the same, the natural result is a sphere. So the roundness of everything in the universe is not just a coincidence. It is a consequence of one of the deepest principles of physics. The universe has no preferred direction. Gravity treats all directions equally, and therefore the shapes that gravity creates are round. This is the secret shape of gravity. Not just a force, but a geometry. Not just a pool, but a sculpture. And the sculpture it creates again and again, at every scale, in every corner of the cosmos, is a sphere. Now let me tell you about some of the strangest round things in the universe. Things that push the concept of roundness to its absolute limits. We have already talked about neutron stars, those incredible objects where gravity has crushed matter to unimaginable densities. But there is something else about neutron stars that is worth exploring: their surfaces. A neutron star's surface is made of iron, but not the kind of iron you are used to. This iron has been compressed by gravity so strongly that its atoms are arranged in a rigid crystal lattice, far denser and harder than any material on Earth. The surface of a neutron star is like a sheet of metal that is millions of times stronger than steel. And yet, even this incredibly strong material cannot resist the gravity of the neutron star. The tallest mountains on a neutron star, the biggest bumps on its surface, are thought to be less than a millimeter tall. Some recent calculations suggest they might be only a fraction of a millimeter. On Earth, mountains can tower almost 9 kilometers above sea level. On a neutron star, the tallest feature might not even be visible to the naked eye. That is how powerful gravity is on these objects. It takes one of the strongest materials in the universe and smooths it out like a pool of water. The gravity on the surface of a neutron star is about 2 billion times stronger than on Earth. If you could stand on a neutron star, which you absolutely cannot because you would be instantly flattened, you would weigh about 150 billion kilograms. The force of gravity would crush every atom in your body. This extreme gravity does something else interesting. It curves space around the neutron star so strongly that you can actually see more than half of its surface at once. On Earth, if you look at a ball, you can only see the half facing you. The other half is hidden around the curve. But on a neutron star, the curvature of space bends light from the far side around toward you. So you can see parts of the back of the neutron star from the front. This means that if you could look at a neutron star, it would not look quite like a normal sphere. It would look slightly strange, as if the surface was somehow wrapping around toward you. This is a direct visual effect of the incredible curvature of space near the neutron star, and it is yet another way in which gravity's roundness shows itself. Now, let us talk about another kind of cosmic sphere, one that you might not have thought about. Shock waves. When a star explodes as a supernova, it sends a blast wave outward into space. This blast wave expands in all directions, and because there is usually no preferred direction for the explosion, the wavefront forms a sphere of hot gas and energy, expanding outward at thousands of kilometers per second. Over time, this expanding sphere sweeps up the gas and dust around the dead star, creating a structure called a supernova remnant. And many supernova remnants are nearly spherical shells of glowing gas, slowly expanding into the darkness. The Crab Nebula, one of the most famous objects in the sky, is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. It is not perfectly spherical because the explosion and the surrounding material were not perfectly uniform, but its overall structure is roughly round because the explosion expanded roughly equally in all directions. Even in death, even in the most violent events in the universe, the tendency toward roundness persists. And speaking of violent events, let us talk about what happens when two neutron stars collide. This is one of the most energetic events possible in the universe, short of a black hole merger. When two neutron stars spiral toward each other and collide, they release an incredible burst of energy. gravitational waves ripple outward through space. A flash of light brighter than 1 billion suns erupts, and heavy elements like gold, platinum, and uranium are forged in the extreme heat and pressure. The gravitational waves from such a collision were first detected in 2017 by the LIGO Observatory, and those waves carried information about the shape of the event. The waves spread outward through space in all directions, like ripples on a pond, but in 3 dimensions, spherical ripples expanding at the speed of light. Even gravitational waves, the very vibrations of space itself, expand in spheres. Now, I want to take you on a slightly different path. We have been talking about gravity and its love of spheres, but I want to talk about what happens when other forces compete with gravity, because the universe is not just gravity. There are other forces at work, and sometimes those forces create shapes that are decidedly not round. Electromagnetic forces, for example. Magnetic fields can shape matter in dramatic ways. The magnetic field of a star can funnel gas into jets that shoot outward from the poles. These jets are not round. They are long and thin, like searchlight beams extending millions of kilometers into space. The solar wind, the stream of particles flowing outward from the sun, creates a vast bubble around the solar system called the heliosphere. This bubble is not perfectly round either. It is pushed and stretched by the interstellar medium, the thin gas between the stars, and by the sun's motion through space. On the smallest scales, the electromagnetic force holds atoms together, and atoms are not perfect spheres either. Well, actually, that depends on how you look at it. The electron cloud around an atom can take various shapes depending on the energy level. Some round, some elongated, some quite complex. But the simplest atom, hydrogen with 1 electron, does have a spherical probability cloud in its ground state. Even at the quantum level, when all else is equal, the sphere appears. But these are exceptions to the general rule, or rather, they are modifications of it. The fundamental tendency is still toward roundness. Gravity still wants spheres. Other forces can distort those spheres, stretch them, flatten them, punch holes in them, but the underlying preference is always there. Take the rings of Saturn. They are flat, very flat, almost impossibly flat. The rings are about 280,000 kilometers across, but only about 10 meters thick in most places. That is like a DVD that is the size of a football field. Why are Saturn's rings flat instead of round? Because they are made of billions of individual particles, each orbiting Saturn on its own. And gravity plus angular momentum conspire to flatten orbiting material into a disk. Any particle that is above or below the main plane of the ring will be pulled back toward that plane by Saturn's gravity. But particles within the plane can orbit freely. So over time, all the material settles into a thin, flat disk. The rings are not a sphere because they are not a single object being pulled together by their own gravity. They are a collection of particles, each in its own orbit, each following its own path through Saturn's curved space. And the collective result is a disk, not a sphere. But Saturn itself, the planet at the center of those rings, is round, because it is a single, massive object pulled into a sphere by its own gravity. The rings are a side effect. The planet is the main event, and this pattern repeats throughout the universe. Individual objects, held together by their own gravity, are round, but collections of objects orbiting a common center tend to flatten into disks. The solar system is a disk. Galaxies are often disks. Even the accretion disks around black holes are disks. It is as if gravity has 2 modes. When it is pulling things together, it makes spheres. When it is organizing things into orbits, it makes disks. But even these disks have a relationship to spheres. A disk is what you get when you take a sphere and flatten it by spinning it. And many disk-shaped structures in the universe are surrounded by spherical halos. Our Milky Way galaxy, for example, has a flat disk of stars where most of the action happens. But it is surrounded by a roughly spherical halo of old stars, globular clusters, and dark matter. The sphere is still there, underneath the disk, like a skeleton under skin. Let us now turn to a question that might seem strange at first. Is roundness the only option for the universe? Could things have been different? Could we live in a universe where gravity prefers cubes or triangles or some other shape entirely? The answer, as far as physics tells us, is no. And the reason goes back to what we said about isotropy. The laws of physics do not favor any direction. If you turn the universe sideways or upside down, the laws work exactly the same way. This means that any force that acts equally in all directions will naturally produce spherical shapes. And gravity is such a force. If we wanted a universe where gravity produced cubes, we would need a universe where certain directions were special, where gravity pulled harder in some directions than others. That would require fundamentally different laws of physics, different mathematics, a different kind of universe entirely. In our universe, the sphere is not just one option among many. It is the only option that is consistent with the fundamental symmetry of the laws of nature. The sphere is inevitable. Now, I want to bring all of these ideas together and paint a picture of the universe as a place of endless, nested spheres. Start with the smallest, an atom. Its nucleus is roughly spherical. Its electron cloud, in the simplest case, is spherical. Go bigger. A drop of water in space forms a sphere due to surface tension. Go bigger still. An asteroid, if it is large enough, becomes a sphere due to gravity. Go bigger. A planet. Round. A star. Round. A white dwarf. Round. A neutron star. Almost perfectly round. Go bigger still. Galaxy clusters, roughly spherical distributions of matter. And at the very largest scale, the observable universe itself, everything we can see, everything we can detect, lies within a sphere about 93 billion light-years across, centered on our location. This is the observable universe, and it is shaped, you guessed it, like a sphere. Not because the universe itself is necessarily spherical, but because light has had a finite time to reach us, and that time defines a sphere of visibility around every observer. Spheres within spheres within spheres. From the quantum level to the cosmic level, the universe is built on round shapes, and at every level the reason is the same. The fundamental forces of nature, especially gravity, treat all directions equally, and when all directions are treated equally, the result is a sphere. This is not just physics, this is beauty. There is something deeply satisfying about the idea that the universe, in all its complexity, keeps coming back to one simple shape. The sphere is the universe's signature, its favorite doodle, its default setting. And every time you see a round planet, a round moon, a round star in the sky, you are seeing the universe express its deepest symmetry. Think about how remarkable that is. The same mathematical principle that makes a soap bubble round also makes Jupiter round. The same geometry that governs a drop of morning dew also governs the shape of a neutron star. The same symmetry that gives a black hole its event horizon also gives the observable universe its edge. The universe speaks one language when it comes to shape, and that language is the sphere. Now, as we come toward the end of our journey, Let me offer a personal thought, something that goes beyond the facts and equations. When I look up at the sky at night and see the moon round and glowing, I used to think of it as just a big rock orbiting Earth, lit up by the sun. And it is that, but it is also so much more. That round shape is the result of billions of years of gravity doing its patient work. It is the visible signature of a force that governs the entire universe. It is a reminder that we live in a cosmos that has rules, and those rules are beautiful. Gravity could have been messy. It could have been chaotic. It could have produced random, ugly shapes, but it does not. It produces spheres, over and over again, at every scale, in every corner of the sky. There is a kind of peace in that, a kind of order. In a universe that often seems vast and cold and empty, the fact that gravity consistently creates beauty, that is something worth knowing. That is something worth carrying with you as you look up at the stars. Every planet you see is round because the universe has rules. Every star is round because those rules are consistent. Every black hole, every neutron star, every moon and comet and world is shaped by the same invisible hand, following the same ancient geometry. And you are here, on a round planet, orbiting a round star, in a galaxy that spins like a round disk, in a universe that may itself be shaped by the ultimate symmetry of all. You are inside the sphere. You are part of the sphere. You are made of atoms that came from round stars that exploded billions of years ago. The roundness of the universe is not just out there, in space, far away. It is in you. The iron in your blood was forged in the core of a round star. The calcium in your bones was created in the spherical furnace of a supernova. The oxygen you breathe was born in the round hearts of ancient suns. You are the universe experiencing its own roundness from the inside. And maybe that is the deepest secret of all. Not just that gravity makes things round, but that gravity made you. And that the same force that sculpts planets and stars and black holes also sculpts the atoms in your body. You are gravity's creation, living on gravity's sphere, looking up at gravity's sky full of gravity's spheres. The universe is round, and so, in a very real sense, are you. Take that thought and hold it for a moment. Let it settle into you like starlight settling through the atmosphere. There is something deeply reassuring about belonging to the same cosmic pattern as the stars, the same shape, the same symmetry, the same ancient geometry that has governed every object in the universe since the very first atoms clumped together in the darkness, billions of years ago. You are part of this story. You have always been part of this story. But there is so much more to this story. We have only scratched the surface of gravity's round obsession. Let us go deeper still, because the details are where the real wonder lives. Let us go back to the very moment a planet is born, not in a general hand-waving way, but in the specific, step-by-step way that scientists have pieced together over decades of research. It starts with a cloud of gas and dust around a young star. This cloud is called a protoplanetary disk. It is a flat, spinning disk of material left over from the formation of the star itself. And within this disk, tiny grains of dust are floating around, bumping into each other. When two grains collide gently enough, they can stick together. This is not gravity at work yet. At this scale, the forces holding the grains together are electrostatic forces and van der Waals forces, the same forces that make dust bunnies clump together under your bed. These forces do not care about roundness. They produce irregular, fluffy clumps, like tiny snowflakes made of rock and metal. These clumps grow. They collide with other clumps. They build up into bigger and bigger objects, first millimeters across, then centimeters, then meters. At this stage, the objects are called planetesimals, and they are utterly irregular, lumpy, jagged, random shapes like rubble piles in space. But as they grow, something changes. At some point, the object becomes massive enough that its own gravity starts to matter. And this is where the magic begins. At first, gravity is just one more force among many. The object is still lumpy because its structural strength can resist gravity's pull. But as the object gets bigger, gravity gets stronger. And eventually, gravity crosses the threshold. It becomes the dominant force shaping the object. When that happens, the object starts to change shape, not suddenly, like a switch being flipped. Slowly, gradually, over millions of years, the tallest peaks on the surface are pulled down by gravity. They collapse under their own weight. The material flows very slowly, like extremely thick honey, toward the center of the object. The deepest valleys get filled in as material redistributes itself, and bit by bit, the object becomes rounder. This process is called gravitational relaxation, and it is happening right now, all over the solar system, on every large body. Even Earth is still adjusting. After the last ice age ended about 10,000 years ago, the weight of the ice sheets pressing down on the land was removed, and the land is still slowly bouncing back, rising by a few millimeters each year. This is called post-glacial rebound. It is gravity, slowly pulling the Earth back toward its preferred shape, its round shape. The speed of gravitational relaxation depends on the material. Ice flows relatively quickly under pressure, which is why icy moons in the outer solar system become round at smaller sizes. Rock flows much more slowly, and metal flows the slowest of all. This is why, for very large rocky planets, the interior needs to be hot enough for the rock to behave like a very thick fluid. The heat helps. It softens the rock and allows gravity to do its sculpting more easily. This is one reason why the early solar system was such an effective forge for round worlds. Everything was hotter back then. The planets were still warm from the energy of their formation. Radioactive elements in their interiors provided additional heat, and this heat, combined with gravity, allowed the planets to settle into their nearly spherical shapes relatively quickly, at least by geological standards. But even today, 4.5 billion years later, gravity is still at work. The Earth is still adjusting to the loss of its ice sheets. The Moon is still slowly changing shape due to tidal forces from Earth. Mars is still settling under its own gravity. Even though its interior has largely cooled, gravity never stops. It is the most patient sculptor in the universe. Now let us explore one of the most amazing consequences of gravity's insistence on roundness. It has to do with what lies beneath the surface of large objects. When a planet or large moon is hot enough inside for its material to flow, gravity does not just pull the object into a round shape on the outside. It also sorts the material on the inside. Heavy stuff sinks to the center. Light stuff floats to the surface. This process is called differentiation. On Earth, differentiation created the layered structure we see today. At the very center is the inner core, made mostly of solid iron and nickel. It is incredibly dense. Around that is the outer core, made of liquid iron and nickel. Then comes the mantle, a thick layer of silicate rock, and on top of everything is the thin crust, the rocky surface we live on. Each layer is roughly spherical, because gravity pulls the heavy stuff down toward the center equally from all directions. The iron sinks straight to the middle, the lighter rock floats on top, and the layers arrange themselves in concentric spheres, like the layers of an onion. This is not unique to Earth. Mars has a core, mantle, and crust. The Moon has them too. Even the icy moons of Jupiter and Saturn are differentiated. Europa, for example, has an iron core surrounded by a rocky mantle, topped by a layer of salty water and covered by a shell of ice. Spheres within spheres, all the way down. And this layered spherical structure has consequences that affect our daily lives. Earth's liquid iron outer core, flowing and churning in the heat of the planet's interior, generates Earth's magnetic field. This magnetic field extends far out into space, forming a protective bubble around our planet that shields us from the solar wind, the stream of charged particles flowing outward from the sun. Without this magnetic field, the solar wind would slowly strip away our atmosphere. Mars is a cautionary tale. Mars once had a magnetic field, but its core cooled and solidified, and the field died. Without that protection, the solar wind slowly eroded Mars's atmosphere over billions of years. Today, Mars's atmosphere is about 1% as thick as Earth's. It is too thin to support liquid water on the surface, too thin to keep the planet warm. The roundness of Earth's interior, the spherical layers created by gravity's sorting, is directly responsible for the magnetic field that makes our planet livable. Gravity shaped the interior into concentric spheres, and those spheres work together like a giant dynamo, generating the invisible shield that protects all life on Earth. So when you look up at the sky and see the round moon, remember, the roundness is not just a pretty shape. It is functional. It is the architecture of habitability. Gravity's spheres are not just beautiful. They are necessary for life. Now, let us explore something else about the roundness of cosmic objects that might surprise you. We have talked about how gravity makes things round, but we have not talked about how precisely we can measure this roundness, and the precision is astonishing. In the 1960s, scientists launched some of the first satellites to precisely map the shape of the Earth, and they discovered something they did not expect. The Earth is not just an oblate spheroid, bulging at the equator due to its spin. It is also slightly pear-shaped. The southern hemisphere is very slightly fatter than the northern hemisphere. And there are gentle bumps and dips in the gravitational field that make the planet's shape slightly uneven in complex ways. This complex shape is described by a mathematical model called the geoid. The geoid is the shape that sea level would take if you could extend the oceans under the continents, and it is a remarkably complex surface. There are highs and lows, places where gravity is slightly stronger or slightly weaker, due to differences in the density of rock beneath the surface. But here is the thing. All of these deviations from a perfect sphere are tiny. The entire geoid varies by less than 200 meters from a perfect sphere. For a planet almost 13,000 kilometers across, that is a variation of about 0.003%. That is like a ball bearing with bumps that are smaller than the size of an atom. So yes, the Earth is not a perfect sphere. But it is so close to a perfect sphere that you would need incredibly precise instruments to tell the difference. Gravity has done an amazingly thorough job, and the Sun is even more impressive. Measurements from the Solar Dynamics Observatory have shown that the Sun's shape deviates from a perfect sphere by less than about 10 kilometers. For an object that is 1.4 million kilometers across, that is a variation of about 0.007%. The Sun is one of the most perfectly round natural objects ever measured by science. This incredible roundness is a testament to the power of gravity acting on fluid material. Gas has essentially no structural strength. It cannot resist gravity at all. and so gravity molds it into an almost mathematically perfect sphere. The only thing preventing perfection is the sun's slow rotation, which adds that tiny bit of equatorial bulge. Stars that rotate faster are less round, but even the fastest spinning stars are still fundamentally spherical. Gravity always wins the shape game. It just sometimes has to share credit with rotation for the exact dimensions. Let us now revisit Einstein's ideas about gravity, because there is another layer to this story that is too beautiful to skip. We said earlier that Einstein showed gravity is the curvature of space and time. But what does that actually mean for the roundness of objects? Consider this. In Newton's picture of gravity, a planet is round because gravity pulls equally from all directions. Simple enough. But in Einstein's picture, the planet is round because the space around it is curved equally in all directions. The planet sits in a spherically symmetric dip in the fabric of space, and the shape of the planet mirrors the shape of the space it occupies. This is a subtle but important difference. In Newton's view, the roundness is caused by a force. In Einstein's view, the roundness is caused by geometry. The planet is round because space itself is round around it. And this geometric picture leads to predictions that Newton could never have imagined. One of those predictions is gravitational lensing. When light from a distant star passes near a massive object like a galaxy, the curvature of space around that galaxy bends the light. The light follows the curved path through the warped space. And because the warping is spherically symmetric, the light is bent equally in all directions around the galaxy. If the alignment is just right, this bending can create a ring of light. The light from the distant star gets bent around the massive object and forms a perfect circle of light on the other side. This is called an Einstein ring, and it is a direct, visible manifestation of the spherical curvature of space. Einstein rings have been observed many times by telescopes like the Hubble Space Telescope and the James Webb Space Telescope. They are real, they are beautiful, and they are proof that the curvature of space around massive objects is spherically symmetric. The roundness of the universe is not just in the objects you can see. It is in the invisible fabric of space itself. The dips and curves and warps in the geometry of the cosmos are round, and they reveal themselves through the bending of light, creating celestial circles that Einstein predicted over a century ago. Let us explore another consequence of this curved space, one that is relevant to our story about roundness: the way that gravity affects time. We mentioned earlier that time runs slightly slower near a massive object. This is called gravitational time dilation, and it is a direct consequence of the curvature of space and time. Near the surface of a neutron star, where gravity is incredibly strong, time slows down dramatically. A clock on the surface of a neutron star would tick about 30% slower than a clock far away in empty space. That is a huge effect. If you spent 1 year on the surface of a neutron star and then returned to Earth, you would find that more than a year had passed for everyone else. Near a black hole, the effect is even more extreme. As you approach the event horizon, time slows down more and more. To an outside observer watching you fall toward a black hole, you would appear to slow down, your movements becoming sluggish, your clock ticking slower and slower. You would appear to freeze at the event horizon, never quite crossing it, your image redshifting until it faded from view. But from your own perspective, you would cross the event horizon in a finite time. You would not even notice it. The event horizon is not a wall or a barrier. It is just the point at which the curvature of space becomes so extreme that escape is impossible. And because this curvature is spherically symmetric, the event horizon is a perfect sphere. Imagine that. A sphere made not of matter, but of geometry. A sphere defined not by atoms or molecules, but by the shape of space itself. The event horizon is the ultimate round object because it is roundness in its purest form. No matter, no energy, just the geometry of the universe curved into a perfect sphere. This is what I meant at the beginning of our journey when I said that gravity is hiding something from us. The secret shape of gravity is not just that it makes planets and stars round. The secret is that gravity itself is round. The curvature of space around any massive object is spherically symmetric. The time dilation is spherically symmetric. The event horizon is a sphere. Gravitational waves expand in spheres. Gravity is not just a force that makes round things. Gravity is roundness. It is the embodiment of spherical symmetry in the physical universe. And every round object you see in the sky is just gravity wearing a costume. A costume made of rock, or gas, or iron, or ice. But underneath the costume, it is all the same. It is all spherical geometry. It is all gravity's secret shape. Now, there is one more thing I want to share with you before we truly wind down for the night. It has to do with the very edge of what science can tell us, the boundary between what we know and what we can only wonder about. We have talked about how the observable universe is shaped like a sphere, centered on our location, extending 46.5 billion light-years in every direction. But what about beyond that? What about the parts of the universe we cannot see? The best current evidence suggests that the universe is, on very large scales, flat, not curved, not spherical, flat. This might seem like a contradiction after everything we have said about roundness. But the flatness refers to the overall geometry of space, the big picture, not the local bumps and dips caused by individual massive objects. Think of it this way: the Earth is round, but if you stand in a large flat field, the ground looks flat. At small scales, the curved surface of the Earth looks flat. Similarly, the overall geometry of the universe appears to be flat, even though individual regions are curved by massive objects. But there is an uncertainty in this measurement. The universe might be very slightly curved. It might, in fact, be an enormous sphere, so large that the tiny patch we can observe looks flat, just as a small patch of Earth's surface looks flat. Some cosmological models suggest that the universe could be a vast, closed sphere, with space wrapping around on itself. In such a universe, if you could travel in a perfectly straight line in one direction for long enough, you would eventually return to where you started. Like walking around the Earth, but in 3 dimensions. We do not know if this is the case. The observations so far are consistent with a flat universe, but they are also consistent with a very slightly curved one. The jury is still out, but the possibility is tantalizing. Because if the universe itself is a sphere, then the story of roundness is not just about the objects within the universe. It is about the universe as a whole. The cosmos itself might be the ultimate sphere, the sphere that contains all other spheres. Imagine that. Every planet, every star, every galaxy, every black hole, every neutron star, every soap bubble, every dewdrop, all of them round objects, all of them sitting inside the grandest sphere of all, the sphere of the universe itself. We do not know if this is true. It might be one of those questions that science can never definitively answer, because the parts of the universe beyond our observable horizon are forever out of reach. But the possibility is there, and it is beautiful. But our exploration is not done yet. There are so many more layers to this story. So many more examples of gravity's round obsession that deserve our attention. Let us keep going. Let us talk about what happens inside a star. Because the interior of a star is one of the most beautiful examples of spherical symmetry in all of nature. We know that stars are round on the outside, but the inside is round too, in layers. At the very center of a star like our Sun is the core. The core is where nuclear fusion happens, where hydrogen atoms are being smashed together to form helium, releasing the energy that makes the Sun shine. The core is incredibly hot, about 15 million degrees, and it occupies roughly the inner 25% of the Sun's radius. Above the core is the radiative zone. This is where energy from the core slowly makes its way outward in the form of photons, particles of light. But the gas in the radiative zone is so dense that these photons cannot travel in straight lines. They bounce around, getting absorbed and re-emitted over and over again. A single photon can take thousands of years, some estimates say up to 100,000 years, to travel from the core to the edge of the radiative zone. The journey is only about 500,000 kilometers in a straight line, but the photon takes an incredibly winding path, bouncing back and forth like a pinball. Above the radiative zone is the convective zone. Here, the gas is cooler and less dense, and energy is transported by convection. Hot gas rises to the surface, cools off, and sinks back down, like a pot of water boiling on a stove. You can actually see the tops of these convective cells on the surface of the Sun. They are called granules, and they make the Sun's surface look like a vast field of bubbling porridge. Each granule is about 1,000 kilometers across, roughly the size of a large country. They last only about 10 to 20 minutes before they fade, and new ones form. And then above everything is the photosphere, the visible surface of the Sun. This is where the light we see actually comes from. It is about 5,500 degrees and is what gives the Sun its yellowish color. Each of these zones is a spherical shell. The core is a sphere. The radiative zone is a spherical shell around the core. The convective zone is a spherical shell around the radiative zone. The photosphere is a spherical shell around everything else. Layers within layers, all spherical, all organized by gravity. And the boundaries between these zones are determined by physics. The boundary between the radiative zone and the convective zone, called the tachocline, occurs at the depth where the temperature drops enough for convection to become more efficient than radiation for transporting energy. This boundary is a sphere, roughly 70% of the way from the center to the surface. Scientists believe that the tachocline is where the Sun's magnetic field is generated. The differential rotation between the radiative zone, which rotates as a solid body, and the convective zone, which rotates at different speeds at different latitudes, creates shearing forces that twist and amplify magnetic field lines. This produces the 11-year cycle of sunspots and solar activity that we observe from Earth. So the spherical layered structure of the Sun is not just a geometric curiosity. It is directly responsible for the magnetic behavior that affects our planet. Solar flares, coronal mass ejections, and geomagnetic storms all trace their origins back to the spherical geometry of the Sun's interior. Round shapes have consequences. Practical, real-world consequences that affect our technology and our lives. Now let me take you to a place we have not visited yet. The space between the stars, the interstellar medium. You might think that the space between stars is empty, but it is not. It is filled with an incredibly thin gas, mostly hydrogen and helium, along with tiny grains of cosmic dust. This gas is incredibly sparse. In the densest parts, there might be about 1,000 atoms per cubic centimeter. In the thinnest parts, there might be only 1 atom per cubic centimeter. By comparison, the air you are breathing right now has about 25 billion atoms per cubic centimeter. So interstellar space is very, very empty, but not completely empty. And in some places, this gas and dust gathers into denser clouds. These are the stellar nurseries, the places where new stars are born. And the shapes of these clouds are governed by, you guessed it, gravity. When a cloud of gas in the interstellar medium becomes dense enough, its own gravity begins to pull it together. At first, the collapse is irregular. The cloud has no particular shape. But as the collapse continues, the central regions become denser and more compact. And because gravity pulls equally from all directions, the densest core of the collapsing cloud tends toward a spherical shape. This is called a Bok globule, named after the astronomer Bart Bok, who first studied them. Bok globules are dark, roughly spherical clouds of gas and dust, typically about 1 to 2 light years across. They are so dense that they block the light of stars behind them, appearing as dark blobs against the bright background of the Milky Way. Inside these globules, protostars are forming. The gas is collapsing, heating up, getting denser, and eventually it will ignite into a new star, a new round object. Born from a roughly round cloud, the birth of stars is the birth of new spheres. And it happens in clouds that themselves tend toward spherical shapes because gravity pulls them together from all sides. Let us now explore something truly mind-bending: the relationship between roundness and energy. In physics, there is a deep connection between the shape of an object and the amount of energy stored in that shape. A sphere is what you might call the lowest energy shape. By that, I mean that if you have a given amount of matter held together by gravity, the configuration that minimizes the total gravitational energy is a sphere. Think about it this way. If you have a lump of material and gravity is pulling it all toward the center, the most efficient packing, the arrangement that puts everything as close to the center as possible, is a sphere. Any other shape would have some material farther from the center than necessary, which would mean more gravitational potential energy stored in the system. This is why gravity wants spheres. Because a sphere represents the state of lowest gravitational energy. It is the most relaxed state, the most settled state, the state where gravity has done as much work as it can, and there is no more energy to release by reshaping the object. This principle is called the minimum energy principle, and it shows up all over physics. Systems tend toward their lowest energy state. A ball rolls to the bottom of a hill. Hot coffee cools to room temperature. And massive objects in space settle into spherical shapes. They are all following the same fundamental tendency, moving toward the lowest energy configuration. And this is related to another beautiful concept in physics: entropy. Entropy is often described as a measure of disorder, but a more precise way to think about it is as a measure of how many different microscopic arrangements are consistent with the observed large-scale state of a system. A sphere is a state of high entropy for a gravitationally bound system, because there are an enormous number of ways to arrange the atoms within a sphere that all produce the same overall shape. So when gravity pulls an irregular object into a sphere, it is not just minimizing energy. It is also maximizing entropy. It is moving the system toward the most probable state, the state that nature overwhelmingly prefers. This is why the roundness of cosmic objects feels so inevitable. It is not just that gravity pulls things into spheres. It is that spheres are the most probable outcome, the most likely shape. the default state of matter under the influence of gravity. Getting from any other shape to a sphere is easy. Getting from a sphere to any other shape requires a lot of energy. Nature is lazy in the best possible sense. It takes the path of least resistance, and the path of least resistance for massive objects leads straight to a sphere. Now let us visit one of the most intriguing objects in our solar system and see how it illustrates these principles. Saturn's moon Titan. Titan is a remarkable world. It is the second largest moon in the solar system, bigger than the planet Mercury, and it is the only moon with a thick atmosphere. In fact, Titan's atmosphere is about 50% thicker than Earth's, and it is mostly nitrogen, just like ours. Titan is round. Of course it is. It is about 550 kilometers across, well above the threshold where gravity forces objects into spheres. But what makes Titan interesting for our story is what lies beneath its orange, hazy atmosphere. Titan has lakes and seas, not of water, but of liquid methane and ethane. These hydrocarbon lakes are mainly concentrated near the poles. The largest of them, Kraken Mare, is bigger than the Caspian Sea on Earth. And here is the connection to our story. These lakes are flat. Their surfaces are level. And the reason they are flat is the same reason that oceans on Earth are flat. Gravity. A liquid surface, in the absence of wind or other disturbances, settles into a shape that is perpendicular to the local gravitational pull. On a round planet, this means the surface of a liquid follows the curvature of the planet. It forms part of a sphere, so even the lakes on Titan are round. Not individually round, but following the round shape of the moon they sit on. The liquid methane in Kraken Mare curves gently along the surface of Titan, part of the spherical shell that gravity demands. And here is something else wonderful. Beneath Titan's icy crust, there is very likely a subsurface ocean of liquid water. The same is true for Jupiter's moon Europa, and possibly for several other moons in the outer solar system. These underground oceans are global. They wrap all the way around the interior of the moon, and they form spherical shells. A spherical shell of liquid water, hiding beneath a spherical shell of ice, surrounding a spherical rocky core, orbiting a spherical planet, which orbits a spherical star. Layers upon layers of roundness, nested inside each other like a cosmic set of nesting dolls. The universe does not get tired of spheres. It keeps making them, at every scale, in every material, under every condition. Spheres are the universe's one-size-fits-all solution to the problem of self-gravitating matter. Now let me tell you about one more extraordinary example of roundness in space, something that combines beauty and violence in equal measure. Planetary nebulae. When a star like our Sun reaches the end of its life, it does not explode in a supernova. That fate is reserved for much more massive stars. Instead, a Sun-like star goes through a gentler, though still dramatic, transformation. As the star exhausts the hydrogen fuel in its core, it begins to burn helium. Its outer layers expand enormously, turning the star into a red giant. The star becomes so large that its outer layers are barely held on by gravity. Slowly, those outer layers drift away into space, forming a shell of gas around the dying star. This expanding shell of gas is illuminated by the hot, exposed core of the star, which is now becoming a white dwarf. The ultraviolet light from the white dwarf makes the gas glow in beautiful colors, greens and blues and reds. And the shape of this glowing shell, often it is a sphere, or close to one, because the star expelled its outer layers roughly equally in all directions, and the expanding, gas forms a roughly spherical bubble. Some planetary nebulae are stunningly spherical. The Cat's Eye Nebula, the Ring Nebula, the Helix Nebula, these are all examples of dying stars surrounded by roughly spherical or ring-shaped shells of glowing gas. They are among the most beautiful objects in the universe. And they are round, or nearly so, because gravity and the symmetry of the dying star shape them that way. Not all planetary nebulae are perfectly round, of course. Many have complex asymmetric shapes caused by fast stellar winds, binary companions, or magnetic fields. But the underlying tendency is spherical. If you strip away the complications and look at the simplest cases, you see spheres. Glowing, ethereal spheres of gas slowly expanding into the darkness. The ghost of a star, still round even in death. There is something deeply moving about that image. A star lives as a sphere. It burns as a sphere. And when it dies, its last breath is a sphere of light and color, drifting through space for tens of thousands of years before it finally fades and disperses. Gravity gives things their shape in life, and that shape persists even in death. Let us shift gears now and talk about something that connects the very large to the very small. The concept of gravitational collapse and what it tells us about the fundamental nature of matter. We have talked about white dwarfs, where electron pressure holds up the star against gravity. And we have talked about neutron stars, where neutron pressure holds up the star. But what is actually happening inside these objects at the atomic level? In a white dwarf, the atoms have been stripped of their electrons. The electrons are floating freely, forming a kind of electron gas. And this gas obeys the rules of quantum mechanics. Specifically, it obeys a rule called the Pauli exclusion principle, which says that no two electrons can occupy the same quantum state at the same time. What this means is that the electrons push back against being squeezed too close together, not because of any electromagnetic force, but because of a quantum mechanical rule about the nature of matter. Electrons simply refuse to be in the same state. And this refusal creates a pressure called electron degeneracy pressure that holds the white dwarf up against gravity. But there is a limit. In the 1930s, an Indian astrophysicist named Subrahmanyan Chandrasekhar calculated that if a white dwarf is more massive than about 1.4 times the mass of the Sun, electron degeneracy pressure is not strong enough to resist gravity. Above this mass, called the Chandrasekhar limit, the white dwarf will collapse further. And what happens then? The electrons get forced into the protons, creating neutrons, and you get a neutron star held up by neutron degeneracy pressure. A similar quantum mechanical effect, but now involving neutrons instead of electrons. And if the neutron star is massive enough, above about 2 to 3 solar masses, even neutron degeneracy pressure fails. Gravity wins completely, and the star collapses into a black hole. This is the progression of gravity's victory over matter. First, atoms resist, then electrons resist, then neutrons resist, and finally, nothing resists. Gravity wins. And at each stage, the object is a sphere, a smaller and denser sphere each time, but always a sphere. This progression is like a series of concentric circles, each smaller than the last. A main sequence star is a large sphere. A white dwarf is a smaller sphere. A neutron star is an even smaller sphere. And a black hole is the ultimate sphere, defined not by matter, but by geometry. Gravity's obsession with roundness intensifies as the collapse deepens. The more matter is compressed, the more perfectly spherical it becomes. A neutron star is rounder than any planet. A black hole's event horizon is rounder than any neutron star. The more extreme the gravity, the more perfect the sphere. This is because at higher densities, the material becomes more fluid, less rigid, less able to resist gravity's reshaping. A rocky planet can have mountains because rock has strength. A neutron star's mountains are millimeters high because the material is less able to resist. A black hole has no irregularities at all because there is no material left to create them, just pure geometry, pure roundness. Let me share another beautiful detail about neutron stars that connects to our theme. When a neutron star spins, it emits beams of radiation from its magnetic poles. These beams sweep around like lighthouse beams as the star rotates. If one of these beams happens to sweep across Earth, we see regular pulses of radio waves. This is a pulsar. The regularity of pulsar signals is extraordinary. Some pulsars are so precise that they rival atomic clocks in their accuracy. The timing of their pulses can be measured to billionths of a second. And this precision is a direct consequence of the roundness of the neutron star. Because the neutron star is so perfectly spherical, its rotation is incredibly smooth and steady. There are almost no wobbles, no bumps, no irregularities to disrupt the smooth spin. The mountains are fractions of a millimeter. The surface is smoother than anything humans have ever manufactured. And so the spin is clean. The pulses are regular. The cosmic clock ticks with astonishing precision. Pulsars have been used for all sorts of scientific purposes because of this precision. They have been used to confirm Einstein's predictions about gravitational waves. They have been used to measure the masses of distant objects. They have been used as cosmic navigation beacons. There is even a proposal to use pulsar signals as a GPS-like navigation system for spacecraft traveling through the solar system. All of this is possible because of roundness, because gravity made the neutron star so perfectly spherical that its rotation is smooth enough to serve as a cosmic clock. Without roundness, pulsars would wobble. Their signals would be erratic. They would be useless as precision instruments. Roundness, in this case, is not just beautiful. It is useful. It is practical. It is a tool that scientists and engineers can rely on, precisely because gravity is so reliable in its insistence on spherical shapes. There is yet another cosmic phenomenon I want to share with you. Gravitational collapse in real time. We have talked about how gravity slowly pulls things into spheres over millions of years. But there are situations where the collapse happens much faster. When a massive star runs out of fuel and its core collapses to form a neutron star or black hole, the collapse happens in less than a second. In less than a second, a core the size of Earth is crushed down to a sphere the size of a city. The matter falls inward at a significant fraction of the speed of light, and the final object, the neutron star or black hole, pops into existence almost instantly, already round. How can gravity create such a perfect sphere so quickly? Because at these extreme densities and temperatures, matter has almost no resistance. The neutrons in a collapsing core behave almost like a fluid. They flow freely. They cannot resist gravity's pull, and so gravity gets its way immediately. There is no waiting for rocks to slowly deform, no waiting for mountains to sink. The material just flows straight into a sphere in a fraction of a second. This is the fastest sculpting that gravity ever does. In everyday life, gravity is patient. It takes millions of years to round off a planet. But in the death of a massive star, gravity is sudden and violent. It creates a perfect sphere in the blink of an eye. And somehow, even in that chaos, even in that violence, the result is beauty. A spinning, pulsing, impossibly dense sphere. Perfect, round, singing its electromagnetic song into the cosmos, Let us also think about the role of angular momentum in shaping cosmic objects. Angular momentum is a measure of how much rotation an object has. It depends on the mass, the size, and the speed of rotation, and it is conserved, meaning it cannot be created or destroyed, only transferred from one object to another. When a cloud of gas collapses to form a star, it starts off rotating slowly, but as it shrinks, it spins faster, just like an ice skater pulling in her arms. This is the conservation of angular momentum. The total amount of angular momentum stays the same, but as the size decreases, the rotation speed must increase to compensate. This is why neutron stars spin so fast. They started out as the cores of large, slowly rotating stars. But when the core collapsed from Earth-sized to city-sized, the rotation speed increased enormously. A star that might have been rotating once every few weeks suddenly finds itself rotating hundreds of times per second. And this rapid rotation introduces the only deviation from perfect roundness that gravity allows: the equatorial bulge. But, as we have discussed, even at hundreds of rotations per second, the bulge on a neutron star is tiny. The gravitational field is so overwhelmingly strong that even rapid rotation cannot significantly distort the shape. Angular momentum also explains why protoplanetary disks are flat, while the objects within them are round. The disk is flat because angular momentum prevents material from collapsing in the plane of rotation. Material can fall inward toward the center, and it can fall toward the midplane of the disk. But it cannot easily lose its angular momentum, so it stays in orbit, forming a flat disk. But within that disk, individual clumps of material that are collapsing under their own gravity have much less angular momentum relative to their own center. So they collapse roughly equally from all directions and form spheres. The disk is flat because of the overall rotation of the system. The objects within the disk are round because each one collapses individually. This is why the solar system has its particular architecture: a flat disk of planetary orbits, organized by the angular momentum of the original solar nebula. And within that disk, round planets, each one sculpted by its own gravity into a sphere. The flat disk and the round planets, two expressions of the same physics, two consequences of the same forces. Angular momentum makes things flat. Gravity makes things round. And together, they create the beautiful, organized structure we see in every planetary system in the galaxy. Let us now contemplate something that bridges the world of physics with the world of philosophy. Why does roundness exist at all? Why does the universe have this particular symmetry? The answer lies in one of the most fundamental principles of physics: the idea that the laws of nature are the same everywhere and in every direction. This principle, called the principle of isotropy, is one of the cornerstones of modern cosmology. If the laws of physics were different in different directions, if gravity pulled harder to the left than to the right, for example, then objects would not be round. They would be elongated in the direction of stronger gravity. But as far as we can tell, the laws of physics do not change with direction. They are the same everywhere. And this means that gravity is the same in all directions, which means that the shapes gravity creates are spherically symmetric. The roundness of the universe is a direct expression of the fact that space has no preferred direction. It is a reflection of the isotropy of the laws of nature. And this isotropy is not something we chose or designed. It is built into the fabric of reality itself. Some physicists have wondered whether this could have been different. Could there be universes where space has preferred directions? Whether laws of physics are not isotropic? Some theoretical frameworks, like certain models of string theory, suggests that extra dimensions of space might exist that are curled up at incredibly tiny scales. If these extra dimensions were to become visible at larger scales, they could potentially introduce preferred directions, breaking the isotropy of space. But in our universe, as far as every experiment has been able to determine, space is isotropic. All directions are truly equal. And so roundness prevails. This is one of those moments where physics touches something deeper. The roundness of planets and stars is not just a physical fact. It is a clue about the fundamental nature of reality. It tells us that we live in a universe where fairness is built into the very laws that govern matter and energy. No direction is special. No orientation is preferred. Everything is treated equally by the forces of nature. And the result is beauty. Spherical, timeless, universal beauty. Let us take one more scientific detour, because there are a few more details that deserve your attention before we bring this journey to a close. Consider the concept of escape velocity. This is the speed at which you would need to travel to break free of an object's gravitational pull. For Earth, the escape velocity is about 11.2 kilometers per second. For the Sun, it is about 618 kilometers per second. For a neutron star, it is over 100,000 kilometers per second, roughly 1/3 the speed of light. And for a black hole, at the event horizon, the escape velocity equals the speed of light itself. That is what defines the event horizon. It is the surface where the escape velocity hits the cosmic speed limit. Now here is the interesting thing about escape velocity and roundness. For a perfectly spherical uniform body, the escape velocity is the same in every direction from any point on the surface. It does not matter whether you launch yourself north, south, east, or west. The speed needed to escape is the same. This is only true because the object is spherical. If the object were some other shape, a cube say, the escape velocity would be different from different points on the surface. From a corner of the cube, you would be farther from the center of mass, and the escape velocity would be lower. From the middle of a flat face, you would be closer to the center, and the escape velocity would be higher. Only a sphere has the property that every point on its surface is the same distance from the center, and therefore, only a sphere has a uniform escape velocity from every point. This is another reason why spheres are special. They are the only shape with perfect gravitational symmetry at every point on their surface, and this symmetry has practical consequences. When we launch rockets from Earth, the gravitational environment is nearly the same regardless of which direction we launch. The slight variations due to Earth's equatorial bulge and uneven density are small, but they exist, and we account for them in orbital mechanics. A truly perfect sphere would make orbital calculations simpler. The real Earth, with its tiny deviations from perfection, adds subtle complexities that engineers must carefully model. Now, let us talk about tidal forces and how they relate to roundness. Tidal forces are the result of gravity not being perfectly uniform. Because gravity depends on distance, the part of an object closer to a source of gravity is pulled more strongly than the part farther away. This difference in gravitational pull stretches the object. You experience tidal forces every day, though you do not notice them. The moon's gravity pulls on the near side of Earth slightly more than it pulls on the far side. This stretches Earth very slightly along the line between Earth and the moon, creating a slight elongation. Not much, but enough to raise the ocean tides. Tidal forces work against roundness. They try to distort spherical objects into elongated shapes, called prolate spheroids, stretched out like an egg. But for most objects in space, the tidal forces from neighboring bodies are much weaker than their own self-gravity. Earth's self-gravity is much stronger than the Moon's tidal pull on it. So Earth remains basically round, with only a very slight tidal bulge. But for objects that are close to much more massive bodies, tidal forces can become significant. The moons of Jupiter, for example, experience strong tidal forces from the giant planet. Io, the innermost large moon, is stretched and compressed by tidal forces as it orbits Jupiter. This tidal heating melts the interior of Io and powers its dramatic volcanic activity, making it the most volcanically active body in the solar system. And yet, Io is round. Despite the enormous tidal forces acting on it, Io's self-gravity is strong enough to maintain a roughly spherical shape. The tidal distortion is there, but it is small compared to the overall size of the Moon. Gravity wins again. The only place where tidal forces can truly overcome self-gravity and destroy roundness is near the most extreme gravitational objects. Near a black hole, for instance, tidal forces can become so strong that they rip objects apart. This process is called spaghettification, and it is exactly what it sounds like. An object falling toward a black hole gets stretched into a long, thin strand by the differential gravitational pull. Spaghettification is gravity at its most destructive, and it is the one situation where gravity actively works against roundness. Near a black hole, gravity is so extreme that it tears things apart instead of pulling them together. The very force that creates spheres everywhere else in the universe is so strong here that it destroys them. But notice something. The black hole itself, the thing doing the destroying, is still round. The event horizon is still a perfect sphere. The photon sphere is still a perfect sphere. It is only the objects falling in that lose their round shape. The black hole itself maintains its spherical perfection even as it shreds everything around it. This is gravity's dual nature. It builds spheres, and it can destroy everything that is not a sphere. It is both the architect and the demolition crew. And in both roles, the sphere is central. The sphere is what gravity makes, and it is what gravity protects, even as it obliterates everything else. Let me also tell you about the role of temperature in gravity's quest for roundness. Temperature is really just a measure of how fast atoms and molecules are moving. In a hot material, the particles are vibrating and bouncing around quickly. In a cold material, they are moving slowly. When rock is cold, it is rigid and strong. It can resist gravity. But when rock is heated, it becomes softer. It starts to flow. At high enough temperatures, rock melts entirely and becomes liquid. This is why the interiors of large planets are so important for their shape. The heat inside a planet, generated by the energy of formation and by radioactive decay, keeps the interior soft. This allows gravity to mold the planet into a sphere more easily. Earth's mantle, the thick layer between the crust and the core, is hot enough that over long time periods, it behaves like a very thick fluid. The rock flows, slowly, incredibly slowly, but it flows. This is what drives plate tectonics. The slow convection of the mantle, hot rock rising, cool rock sinking, drives the movement of the tectonic plates on the surface. And this flow is what allows gravity to maintain Earth's spherical shape over geological time. If the mantle were completely solid and rigid, the Earth might accumulate larger irregularities over time. But because the mantle flows, any large-scale irregularities get smoothed out. Mountains get worn down. Valleys get filled in. The surface slowly, perpetually, drifts back toward the sphere that gravity demands. On a dead, cold planet or moon, without internal heat, This smoothing process stops. The object freezes in whatever shape it had when it cooled. Small irregularities can persist forever, but even on these cold, dead worlds, the overall shape is still spherical, because the initial formation happened when the material was hot and fluid. The Moon is a good example. It has been geologically dead for about 3 billion years. Its interior has cooled and solidified. There are no more volcanic eruptions, no more tectonic movements. And yet the Moon is round, because it formed when its material was hot and soft, and gravity pulled it into a sphere before it cooled down. The roundness was locked in early, even though the smoothing process has long since stopped. Let me share one more scientific concept with you. It is related to everything we have discussed, and it brings the story of roundness to a satisfying philosophical conclusion. The concept is the virial theorem. The virial theorem is a result in physics that relates the average kinetic energy of a system of particles to its average potential energy. For a system held together by gravity, like a star or a cloud of gas, the virial theorem says that the system will settle into an equilibrium state where the kinetic energy, the motion of the particles, is related in a specific way to the gravitational potential energy. This equilibrium state is what we have been calling hydrostatic equilibrium, and the shape of this equilibrium, for a gravitationally bound system with no preferred direction, is a sphere. The virial theorem is a mathematical statement of what we have been describing in words throughout this journey. It tells us that gravitationally bound systems naturally evolve toward a specific state, a balanced state, an equilibrium state, and that state is spherical. It applies to stars, it applies to planets, it applies to globular clusters, those beautiful, tightly packed spherical collections of old stars that orbit the Milky Way. It applies to galaxy clusters. It applies to the hot gas filling the space between galaxies. The virial theorem is gravity's instruction manual. It tells matter how to arrange itself, and the instruction, every time, is to form a sphere. Now, there is one last thought experiment I want to share with you. Imagine you could watch the universe evolve from the very beginning, all the way to the far future, but in fast forward. Speed it up so that billions of years pass in minutes. What would you see? At first, a hot, smooth, almost featureless glow. The early universe, almost perfectly uniform, almost perfectly round in every direction. Then, as you watch, tiny ripples appear. Dense regions get denser. Material starts to clump together, and wherever it clumps, it forms spheres. Spheres of gas that ignite into stars. Spheres of rock that cool into planets. Spheres within spheres, organized into disks by rotation, but individually, always round. You would see stars born as spheres, living as spheres, dying as spheres. You would see their remnants, white dwarfs and neutron stars and black holes, all spherical. You would see galaxies form, with spherical halos of dark matter surrounding flat disks of stars. You would see galaxy clusters, roughly spherical collections of thousands of galaxies. And if you watched long enough, trillions of years into the future, you would see the universe grow dark and cold, stars burning out, galaxies drifting apart, matter decaying, until eventually, far in the future, the universe might be nothing but a vast, cold emptiness populated by the drifting remnants of dead stars and evaporating black holes. And those final remnants, those last objects in the dying universe, they would still be round, because gravity never forgets its favorite shape. From the first moments of the universe to its last dying gasps, the sphere endures. Now, as we truly begin to wind down our journey, let me paint one more picture for you. Imagine you are floating in space, far from any star or planet, just you and the darkness and the stars. You can see in all directions, above, below, in front, behind. Every direction looks the same. Stars everywhere, in every direction, roughly the same number, roughly the same brightness. This is what isotropy looks like. The universe on large scales looks the same in every direction. And this sameness, this cosmic equality, is the reason everything is round. Now imagine you start flying toward a star. As you get closer, the star grows larger. It is round, perfectly, beautifully round. You can see its surface churning with convective cells, its corona glowing faintly around the edges. It is a sphere of fire, balanced between the inward pull of gravity and the outward push of fusion energy. You fly past the star and approach a planet. It too is round. You can see its atmosphere, its oceans, its clouds, all curving gently around the sphere. The atmosphere thins as it rises, each layer slightly less dense than the one below it. Spherical shells of gas getting thinner and thinner until they fade into space. You fly closer and land on the planet. You stand on its surface and look up. The sky is a dome above you. The horizon curves gently in all directions. And if you could see through the ground beneath your feet, you would see layers of rock and metal, each one a spherical shell, each one sorted by gravity, heaviest at the bottom, lightest on top. You are standing on a sphere, surrounded by spheres, inside a universe that might itself be a sphere. And all of it, every bit of it, was made by gravity, the most patient, most persistent, most universal force in nature. The sculptor of the cosmos, the secret round maker. But before we wrap this story up, I want to take a few more quiet detours through the cosmos, because the examples of roundness are truly endless, and each one reveals something new. Let us talk about the cosmic microwave. Background, the CMB. This is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and for light to travel freely through space for the first time. Before that, the universe was so hot and dense that light could not travel very far without being absorbed and re-emitted by the thick soup of particles that filled all of space. When that light was released, the universe was almost perfectly uniform. Almost the same temperature everywhere. Almost the same density everywhere. But not quite. There were tiny fluctuations, tiny differences in temperature from one spot to another. And these fluctuations were the seeds that would eventually grow over billions of years into the galaxies and galaxy clusters we see today. Now here is what is fascinating about the CMB in the context of our story. The fluctuations in the CMB are not random. They have a specific pattern. And that pattern is related to spherical harmonics, the mathematical functions that describe vibrations on the surface of a sphere. Think about a bell ringing. A bell has a specific shape, and when it rings, it vibrates in specific patterns. These patterns are called modes of vibration, and they depend on the shape of the bell. The early universe was like a bell. It was vibrating, oscillating, with regions of slightly higher and slightly lower density. And because the universe on large scales is roughly spherical, or at least the observable universe is, these vibrations follow the mathematics of spherical harmonics, the same mathematics that describes the vibrations on the surface of a sphere. The patterns, in the CMB are essentially the ringing of the spherical early universe. They are the cosmic overtones of the Big Bang, frozen in time, visible today as tiny temperature differences in the microwave sky, and the fact that they follow spherical harmonics is yet another expression of the universe's deep connection to spherical geometry. Cosmologists use these patterns to extract incredibly precise information about the universe, the age of the universe, the amount of matter and energy it contains, the curvature of space, the rate of expansion. All of this is encoded in the spherical harmonic patterns of the CMB, the ringing of a cosmic sphere, telling us the deepest secrets of the universe. Let us now turn to another beautiful example. Gravitational waves. When two massive objects, like black holes or neutron stars, orbit each other and eventually merge, they create ripples in the fabric of space and time. These ripples are called gravitational waves, and they spread outward from the source in all directions. In what shape? A sphere, of course. Gravitational waves expand as spherical wavefronts, moving outward at the speed of light. They are like the sound waves from a bell, but instead of vibrating air molecules, they are vibrating the very fabric of space itself. They stretch and squeeze space as they pass, making distances slightly longer in one direction and slightly shorter in another. When LIGO detected gravitational waves for the first time in 2015, it was one of the most important discoveries in the history of physics. It confirmed a prediction that Einstein had made exactly 100 years earlier. And the waves that LIGO detected had traveled across the universe as expanding spheres, getting weaker as they spread out, before finally reaching Earth and causing the tiniest measurable distortion in LIGO's detectors. The distortion was incredibly small, about 1,000th the diameter of a proton. That is how faint gravitational waves are by the time they reach us from distant cosmic events. But the fact that we can detect them at all is a triumph of human ingenuity and engineering. And the fact that they travel as spherical waves is yet another testament to the isotropy of space. Gravitational waves, like light, like all radiation, expand in spheres. Now, let me share something about the relationship between roundness and darkness, because one of the most mysterious substances in the universe, dark matter, also seems to love the sphere. Dark matter makes up about 27% of the total mass and energy of the universe. We cannot see it. We cannot touch it. We do not even know what it is made of. But we know it is there because of its gravitational effects. Dark matter pulls on regular matter, bending light and shaping the orbits of stars and galaxies. And the distribution of dark matter around galaxies is roughly spherical. Our Milky Way galaxy is a flat, spinning disk of stars. But surrounding this disk is a much larger, roughly spherical halo of dark matter. This halo extends far beyond the visible disk of the galaxy, out to distances of several 100,000 light years. It is the gravitational skeleton of the galaxy, the invisible framework that holds everything together. Without the dark matter halo, the stars in the outer parts of the Milky Way would not orbit as they do. They would be moving too fast for the visible matter alone to hold on to them. They would fly off into intergalactic space. But the dark matter, distributed in its spherical halo, provides the extra gravitational pull needed to keep the galaxy together. So even the invisible stuff, the mysterious dark matter, follows gravity's preference for spherical shapes. It wraps around galaxies in spherical halos. It clusters in roughly spherical distributions within galaxy clusters. It fills the invisible scaffolding of the cosmic web in patterns that, on large scales, tend towards spherical symmetry. The universe's love of roundness runs so deep that even the things we cannot see are round. Now let us talk about one more aspect of the roundness of the cosmos, the concept of the photon sphere around a black hole. We have already discussed the event horizon, the spherical boundary from which nothing can escape. But outside the event horizon, there is another important sphere, the photon sphere. This is the distance from the center of a black hole where gravity is so strong that light can orbit the black hole in circles. For a non-rotating black hole, the photon sphere sits at 1.5 times the Schwarzschild radius. At this distance, a photon traveling sideways relative to the black hole will be captured into a circular orbit. It will literally orbit the black hole, going around and around at the speed of light. These orbits are unstable. The slightest perturbation will cause the photon to either fall into the black hole or escape into space. But they exist, and they form a sphere of light around the black hole. When the Event Horizon Telescope captured its famous image of the black hole in M87, the bright ring of light in the image was related to this photon sphere. The light was coming from hot gas near the black hole, but the bright ring was formed by light that had traveled along or near these photon orbits before escaping toward us. So black holes are not just defined by one sphere, they are defined by multiple spheres. The singularity at the center, which, for a non-rotating black hole, is a point, but we can think of it as a sphere of zero radius. The event horizon, a larger sphere, and the photon sphere, an even larger sphere. Concentric spheres of increasing radius, each defined by a different gravitational threshold. Even in the darkest corners of the universe, where light cannot escape and matter is crushed out of existence, gravity still builds its favorite shape. Sphere upon sphere upon sphere. Let me also touch on something that might seem trivial, but is actually deeply connected to our story. Raindrops. You might think that raindrops are shaped like teardrops, with a pointed top and a round bottom. That is how they are usually drawn in cartoons and diagrams. But that is not how they actually look. In reality, small raindrops are nearly perfect spheres. Surface tension, the same force that makes soap bubbles round, pulls the water into a ball. For small drops, surface tension easily overcomes the effects of air resistance, and the drop is round. Larger raindrops get flattened on the bottom by air resistance as they fall. They start to look like hamburger buns, round on top and flat on the bottom. And very large drops become so flattened that they eventually split into smaller drops, which then become round again. So even in the mundane everyday world, the sphere is the default shape. Water wants to be round. Not because of gravity, in this case, but because of surface tension. And the mathematics is the same. A force acting equally in all directions produces a sphere. The sphere is nature's answer to the question, what shape should I be? It is the shape of least effort, the shape of maximum efficiency, the shape that minimizes surface area for a given volume, the shape that minimizes gravitational energy for a given mass, the shape that nature returns to again and again, whenever no other force imposes a different structure. Let us visit one more exotic object before we conclude: quasars. Quasars are the most luminous objects in the universe. They are powered by supermassive black holes at the centers of distant galaxies, black holes that are actively feeding on gas and dust. As material falls toward the black hole, it forms an accretion disk and heats up to incredible temperatures, emitting more light than the entire rest of the galaxy. The black hole at the center of a quasar is a sphere defined by its event horizon. The accretion disk around it is flat, a disk of superheated gas spiraling inward. But the radiation from the quasar, the light and energy pouring outward, expands in a roughly spherical pattern. The quasar shines in all directions, its light traveling outward in expanding spherical wavefronts, reaching across billions of light-years of space, and surrounding the quasar. The gravity of the supermassive black hole curves space into a spherically symmetric dip, bending the light of background objects and creating gravitational lensing effects that reveal the spherical geometry of space-time itself. Even the most violent, most energetic, most extreme objects in the universe are organized around spheres. The sphere is not gentle. It is not just the shape of peaceful, sleeping planets. It is the shape of the most terrifying objects in existence. Black holes, neutron stars, quasars, supernova remnants. Gravity does not care about our feelings. It does not care whether it is sculpting a quiet garden world or a screaming maelstrom of destruction. Either way, the result is the same shape. Either way, the answer is a sphere. Now, let me tell you about one final haunting example of roundness, the cosmic horizon. We live inside a sphere, not a physical sphere, but a sphere defined by the speed of light and the age of the universe. Light has had 13.8 billion years to travel since the Big Bang, and that means the farthest objects we can see are about 46.5 billion light-years away, in every direction. This defines a sphere, centered on us, called the observable universe. But here is the haunting part. Beyond this sphere, there is more universe. We just cannot see it yet. Light from those regions has not had time to reach us. And from the perspective of an observer on the other side of the universe, their observable universe is a different sphere, centered on them. Our sphere and their sphere overlap, but neither one contains the whole universe, so the universe is full of overlapping spheres of visibility. Every point in the universe is the center of its own observable sphere. And none of these spheres is more special than any other. Every observer, everywhere, sees the universe extending out in a sphere around them. This is the ultimate expression of the isotropy of the universe. Every point is the center of its own sphere. Every direction looks the same. There is no special place. There is no edge, just spheres within spheres within spheres, stretching out in every direction, forever. And that image of infinite overlapping spheres, each one centered on a different point in the vastness of space, each one containing billions of galaxies, each one expanding as the universe ages and light has more time to travel. That image is the deepest picture we have of the shape of reality. The universe is made of spheres. It is filled with spheres. It is defined by spheres, and it may itself be a sphere. That is roundness taken to its cosmic extreme. That is gravity's secret shape, revealed not just in the objects we can touch, but in the very structure of space and time and existence itself. That is the story of why everything in the universe is round. It is the story of gravity, of symmetry, of geometry, of the fundamental nature of space and time. Now, let me bring this back to something personal, something you can take with you as you drift off to sleep. The roundness of the universe is not abstract. It is not just mathematics and physics. It is real. It is tangible. You can see it. Step outside on a clear night and look up. The moon is round. Every star you see is round. Although they are so far away they look like points of light. The planets, if you know where to find them, are round disks in a telescope. But there is something else you can do, something simpler. Pick up a ball, any ball, a tennis ball, a baseball, a marble. Hold it in your hand. Look at it. That shape, the smooth curve, the lack of edges, the way it looks the same no matter how you turn it, that is the shape of the universe. the same shape that gravity gives to planets and stars, the same shape that surface tension gives to bubbles and drops, the same shape that the mathematics of symmetry says is the most fundamental, the most basic, the most natural shape in all of reality. When you hold a ball, you are holding the secret of the cosmos in your hand. And when you look at the moon, you are seeing that secret writ large across the sky, a secret billions of years in the making, a secret sculpted by gravity, verified by Einstein, expressed by every massive object in the universe. Everything is round because the universe has no preferred direction. Everything is round because gravity pulls equally from all sides. Everything is round because the geometry of space itself is symmetric. Everything is round because round is the shape of fairness, of balance, of equality. The universe does not play favorites. It does not pick one direction over another. It treats everything the same. And the result is beauty. Perfect, spherical, timeless beauty. So close your eyes now. Picture the Earth floating in space, blue and white and green, round, impossibly, beautifully round, and around it, the moon, round, and beyond that, the sun, round, a golden sphere of fire balanced between gravity and fury, and beyond that, billions of stars, all round, all burning, all obeying the same ancient law, gravity's law, the law of the sphere. Let that image carry you into sleep. Let it remind you that you live in a universe that makes sense, a universe with rules. A universe where the same force that keeps your feet on the ground also sculpts the stars into perfect spheres. A universe where beauty is not an accident, but a consequence of the deepest symmetries of nature. The universe is round, and tonight, as you sleep on your round planet, orbiting your round star, in your round galaxy, inside your round observable universe, you are surrounded by roundness, cradled by it, protected by it, part of it, sweet dreams, and clear, star-filled skies. If this journey through the roundness of our world helped you see the stars a little differently tonight, consider subscribing to join our sleepy community. We will be here whenever you need us, exploring the wonders of the cosmos together, one beautiful night at a time. Good night. If you made it here, you already know what this feels like, that quiet, that drift. But every night it ends. The video stops, the silence wakes you, and you're reaching for your phone at 3 a.m., choosing something new when all you wanted was to stay asleep. Beyond the Stars was made for that moment. 5 deep sleep experiences, hours long, no ads, no endings, just the night, all the way through. Yours tonight for a one-time purchase. Begin now at mycosmicdrift.com.